Hey, it's Mr. Aaron. Today we want to talk about applications dealing with growth and decay of exponential functions. And we've talked about these before, but we want to write them so that we're solving a little bit more difficult now for the rate or time. Which, remember, these were in our formulas the variables a or t. Okay. So if you remember, the population function looked like p of t equals p naught times a to the t, where a was a rate, t was a time, p naught was a starting amount, and P of t was the actual ending amount. So I want to do an example here. We'll say given an actual function, which will be P of t equals 50,000 times 1.24 t. So we've got an initial population of 500,000, and we've got a function that calculates future population in years. We're going to ask ourselves, how many years will it take the population to triple? So we got a function that calculates the population in the future, 2 years from now, and we're trying to figure out how long it takes the population to triple. So let's kind of look at our function. We know that we're starting at 50,000, so we just need an ending amount that would be triple that. So that would be 150,000. So we can set that function up into an equation. 150,000 equals 50,000 times 1.24 to the t. So the only thing that's we don't know right now is t. So we can solve for that. So the first thing we would do would be to divide out the 50,000 coefficient. So we'd have 3 equals 1.24 to the t. So there we see the tripling. Okay, doesn't matter what we started with. If we're tripling and we divide that out, the ending amount would be 3 times it. Not 3 times it, but it would be 3. The ratio would be. So here we need to be able to solve for t, and since it's in an exponent position, we'll convert it over to a log form. So it'll be log base 1.24 of 3 equals t. So when we write something in in log form, the exponent goes on the side by itself. So we want to continue this and solve it. We're going to use the change of base on the left-hand side, and we'll change log base 1.243 to log 3 over log of 1.24. So I'm going to pick up a calculator and put that in. Log 3 divided by log of 1.24. In this scenario, I get 1.511 years. So if I put this in correctly, that rate of growth, the 1.24 up here, causes it to triple every 5 years or so. Okay. So let's do a second example. And let's do it with decay. And you remember when we do the growth decay, I'll just stick with decay because that makes more sense for what we're doing. We use the function a of t equals a naught times little a raised to the t. Same as the population formula, but just a different application, a different discipline, chemistry instead of biology. So now we're talking about a different variable. Okay, so let's say something similar here. Let's say we want to ask a question. We might be given a function. A of t equals 250 times 0.73 to the t. So this is a very similar example. But we're talking about here possibly in an application, we may start with 250 grams of a material. And if it's radioactive, it's going to decrease in material. So plugging in a value for t up here, depending on what time is measured in, if we say years, we could figure out how much would be left after so many years. So let's say how much is left after, excuse me, that's not what I wanted to ask. That's what we did in the previous videos. So erase that. We're getting some freeze up here. Sorry, so the question I actually wanted to ask is, what is the half-life of this material? So we've got a function that will calculate how much is left after any given amount of time, but what we're asking is, how long would it take to cut the material in half? So if it's radioactive and it's losing mass by giving off material through radiation, then the question is, how long before we have half of this left? And even if you're not given a starting amount, you can still do this. Okay, so we have a starting amount of 250, but if we want to actually solve the equation, we would say that how long would it take it to cut in half would be how long it would take it to become 125. So we get the equation 125 equals 250 times 0.73 to the t. Just like before, we will divide the 125 by the 250 and we'll have a half over here equal to 0.73 t. So once again, we'll convert this over to a log. Log base 0.73 of 1/2 equals t. We'll use change of base. Log of 1/2 over log of 0.73 equals t. That's still an exact answer, but we're going to go to a calculator. So we get some reasonable number. Log of 0.5 divided by log of 0.73. And I get 2.2, if this is in years. So this is a silly little question, but in the scope of things, we were able to solve it. Okay. So in these first two examples, we solved for the time it would take for something to happen. So let's say we kind of change our equation up, and we're still going to go with the decay model. A of t equals a naught times a to the t. So let's ask this question. You start with 700 cells and you give it like some type of medication, and in 6 hours you have let's say a nice number, 50 cells left. So if you're assuming this is a exponential decay problem, we can write our function. So we know that the ending amount here is 50 and the starting amount was 700. What we don't know is the rate, the A, but we do know the time it takes for that to happen, which is 6. Okay, so a little bit different problem. So what we're going to do here is we can divide out the 700. So 50 divided by 700 is not the prettiest number, so just for sake of arguments, I'll make it 5 over 70. Let's see, can we make that even better? We can make that 1 over 14. That's a nice thing, but that will be equal to a to the 6. So if we do this, we haven't converted anything. We're just trying to get our a by itself. So let's just kind of take another look at it. We've got 1 over 14 equals a to the 6. And we want to get the a by itself. It's right now raised to the 6th power. So what we can do is take the 6th root. If we do that to one side, we'll do it on both. So the exact answer here would be a equals, and technically a positive and negative. But what good would that do us? Because we know we're not going to have a negative time. But it would be the 6th root of 1 over 14. Now let's go to a calculator and see if we actually got this. Okay, so 1 divided by 14 raised to the 1/6. I get 0.644. So that is the rate. Now that we have that, we could write the function of this, still starting with 700 if we wanted to, but we could write it to figure out how many would be left in 7 hours or 8 hours or 20 hours. So there's a lot of things we can solve for here. All right, thank you.